So Louise Nielsen, she will talk about NIRPS, and she will talk from La Silla, which is always fancy. Maybe she shows us the instrument. No, she's in the control room.
All right, thank you very much. Good morning and afternoon. Yes, I'm sitting right next to the NIRPS machine during the calibrations while we're doing this talk, so it's very on theme for today. So I'm just gonna dive straight in, and hopefully, Carlo, you'll let me know if I'm going over time. Yeah, I'll keep an eye on it myself as well.
Feel free.
So yeah, NIRPS in a nutshell is a cryogenic, high resolution fiber-fed shell spectrograph built for getting radial velocity measurements of M dwarfs, but I'm sure that there's a lot of other science that can be done with it as well. We'll get into that later. So it's on the ESO 3.6 meter telescope. And at the moment, the DTO has been awarded 40% of the time over 5 years, but there's still a lot of time for guest observation programs as well. What's very new about NIRPS is that it's AO assisted, meaning we're using an AO system to feed our very small fiber, because in the near-infrared you either need a very large spectrograph or a very small fiber to feed your spectrograph to obtain a high resolution. The spectrograph operates in Y, J, and H band, and we have 2 different modes using 2 different size fibers that give 2 different resolutions. And the numbers I have on the screen here, 82,000 and 75,000, those are the most, let's say, updated numbers on the actual resolution that we are achieving in the instrument. The top level requirement is a very high RV precision of 1 meter per second. I would say we're not quite there yet, but I'll show some results from the previous commissionings. And maybe also, if we have time, I can say something about how we can get to the 1 meter per second accuracy over time, or precision over time. So for those who know the 3.6 meter telescope in La Silla, we already have a high resolution spectrograph called HARPS that operates in the visible, and NIRPS will be operating simultaneously with HARPS. So we have a dichroic beam splitter in the path, and this way you can get both a near-infrared and a visible spectrum of your target in one shot. So that's quite nice. So just to let you know that the NIRPS system consists of several subsystems. So we have the front end where we have the AO system as well that's feeding, sending light to both HARPS and NIRPS and feeding the NIRPS fiber with the AO system. Then we also have the fiber link where, as I said before, we have these 2 different modes we can observe in. And there's some specs on the 2 different fibers here for those who are interested. We also have a dedicated calibration unit for NIRPS, so we're using a simultaneous Fabry-Perot to get a simultaneous wavelength calibration during our observations. You can also choose to observe the sky, which at the moment seems to be a very good option as the spectrograph is very stable over time. And we also have other calibration lamps in the calibration unit, but I won't go into those. And then, of course, the spectrograph itself, which is probably the most exciting part to talk about today. The status of NIRPS is that there was a kickoff meeting back in 2016. We had first light here in La Silla in June last year. It followed very soon after that of a change of the grading, as we got offered a grading that had better specs than the original one. So we quickly did that back in July, and then the instrument was offered to the community for period 111 back in August last year, and again we're now offered again in period 112. And at the moment we're in the midst of the final commissioning, which will finish Saturday next week, and then we should be ready to go. In the future, there is an opportunity of getting a laser frequency comb in the calibration unit, and that's something that is underway. So the NIRPS science cases, I've sort of highlighted 3 main cases here, and that's the radial velocity planet search. So this would looking for the Doppler motion of a star induced by a planet around it by using this high resolution spectroscopy. Using also radial velocity method, we can get the masses of transiting planets. So this is a very big field now, where from the transit you will get the size of the planet, and then by doing follow-up spectroscopy, you can get the mass of the planet, and thus says something about its internal structure and composition. Exoplanet atmospheres are a growing field, and it's a very large part of the NIRPS DTO as well, where we are measuring the light filtered through the planet's atmosphere as it transits the star. But there is also the option of doing reflected light with NIRPS, and when you're doing reflected light from the planet, it doesn't necessarily have to be transiting. So that's some very exciting science cases that have not been done in length from the ground before. But of course, there are also other sciences to be done with NIRPS. So I'm thinking stellar physics here, and hopefully a lot of people on this call could have a science case that they can think up that I have not even thought about. So to show some very preliminary results, so this is what the spectral coverage looked like for NIRPS. So this is a picture of our nearest neighbor Proxima. And as you can see, we have a gap in the middle. So this, oh, you can't see my mouse, but it's fine. We have a gap in the middle where we have absorption in the fiber itself. So these are 2 orders that we lose on our shell grating. And then most of the other features you can see here are atmospheric. So we're very much affected by absorption in our own atmosphere from water and oxygen and CO2. And of course, this is something that you would have to correct in order to get very high precision radial velocities. So here I have
Louise,
a
we
radial
do see the
velocity
mouse
time
if you
series.
need to. If you want to
Sorry?
use it, we do see the mouse. So
oh, really? Okay, I
really
don't see my mouse, so I won't attempt to use
Okay.
it. Here we see a radial velocity time series of Proxima again, so the same star as before. And I apologize that the points are a little small, but this is really on-the-fly data I'm showing you right now. But just to, I think the numbers here to pay attention to are the 2 different modes. So HA, which is our high accuracy mode, so using a small fiber. HE is our high efficiency mode, so using a larger fiber, but you degrade a little bit in resolution. And what we put on the slide here is the RMS of the data points that we have here, spanning 1, 2, 3, 4, 5 days of RV monitoring. So this is very promising, but of course we still have some work to do to really get to the 1 meter per second. And here's another case where we've been doing radial velocity monitoring of very high cadence, staying on the same target, where we get 1.5 meter per second RMS over a few hours, and less than a meter per second point-to-point RMS in this plot here. So observing with NIRPS both in P111 and 112 will probably mainly take place at the telescope. So since we're dealing with a new instrument, we also have a system that we're still making sure is robust enough for the users to use. So we highly recommend inexperienced users to come to La Silla and observe in visitor mode, or if people prefer not to come to La Silla, there is the option of contacting someone else observing and use this La Silla eavesdropping mode to receive training before you go in person. At the telescope, the data is reduced in real time, and is also archived in real time. So if you're sitting at home observing in DVM, you should be able to check your data on the fly as well, and perhaps adapt your strategy if needed. The pipeline is based on the Espresso DRS, for those who are familiar with that, and it's publicly available within the ESO-REX package. And the pictures you see here are some pictures from last night where we were observing. So on the top, you have the AO on one screen, and then you have a raw spectrum of the other side where there's been zoomed in on a specific region that has an OH skyline right next to it. And the bottom picture is the online trigger we have running here at the telescope that will show you the CCF of your star, of your spectrum, and your velocity, and also give you a lot of quality control information on the fly, so you can really check if your data is up to standard while you're observing. Let me check the time. I still have some. Very good. So I think I went through my slides very quickly, so we'll have a lot of time for questions if there are any. So just to let you know that there's a lot of useful information on the ESO pages, so do go read the user manual. A lot of the information I presented now has been taken straight from the user manual, but we also have the pipeline instructions and so forth on the ESO page, of course. There's also a very extensive list of targets that are blocked for the DTO in period 112, so do go check that the list of targets before you write your proposal. And then I should definitely say that we have an ESO ETC ETC now that works for HARPS and NIRPS combined. I've been validating it so far, and it's been a real pleasure to use. For those who are interested in atmosphere studies, a very nice feature of the new ETC is that you can put in the velocity of your target and the barocentric velocity of the day you're observing, and you can simply simulate the skylines for a given observation, meaning that if you want to make sure you don't have a OH sky emission line on top of a very important spectral feature in your spectrum, you can check this with the ESO ETC and thus check which dates would be the best to observe. So given I have a little bit extra time, I can say something about this slide here. So this is really trying to say something about the challenges towards getting to the goal of 1 meter per second. So I think telluric correction is something that anyone who's ever operated in the near-infrared are familiar with. And I want to say that the plan is to have here at the telescope an on-the-fly telluric correction that will give you telluric corrected radial velocities at the telescope, and this is something that we're implementing this commissioning. But a more sophisticated approach using either, for instance, a PCA approach may be needed for publication in the future, or may be able to optimize the radial velocity slightly. And we are also observing telluric standard stars at a range of BERVs and air masses, and this will probably be part of the nominal operation in the future as well. M dwarfs, especially the late type M dwarfs, those spectra have mainly blended lines. So thus, a CCF approach may not be the most optimal approach for extracting radial velocity information from the spectrum. And that's why a lot of other groups have been working on line by line techniques or other types of template matching techniques. So this is something that may perform better than what we have currently implemented in the on-the-fly pipeline. And then I think the last point I have here is modal noise, and we call it modal noise, but it is really not. It's not actual modal noise, but this is something that may be quite specific to NIRPS right now. But it's a fringe-like structure we see on our spectrum in the very reddest parts of the orders, and it appears to be stable over days and perhaps also over weeks. And we are now working on calibrating this modal noise out by using very high signal-to-noise observation of stars that have no spectral features. So those will be telluric standards, and that seems to be working very well. But these are the 3 points I can think of that we're still improving on before we can really get to this 1 meter per second precision in the near-infrared. So with that, I will take some questions. Thank you.
Thank you, Louise. Yeah, so we'll unless if there are urgent question or question that arise immediately, otherwise we postpone to after the last talk.